See, first of all, obviously, it's welcome back today to our session. Now, I keep forgetting, is it a 12th or 13th session? It's you guys can look up the calendar. But to give you an idea what we're going to do next, we're going to move after this. Today is our final day for document AI and computer vision. After that, we'll move on to code generation. And after that, the remaining weeks will give to just you guys doing a capstone project and showing the results. Does that make sense, guys? You guys have to plan out. So what I want you to do today at some point is form your little groups, your teams, and propose a project. Today, you should at least propose a project that you'll do, which utilizes a significant proportion of whatever it is that you have learned so far. Right? Make it meaningful, make it realistic, make it useful, make it something that you would like to showcase, perhaps put on GitHub, perhaps talk in your within your company, or talk in your job interviews in case you're looking to shift jobs. Make it worthwhile. In other words, that's how you learn. If you shoot to make a project really worthwhile and useful and with real world impact, then you'll make it useful. So that will be our schedule. Now, the topic today is a continuation of document AI. Last week, we learned about document AI. It was an experiential learning day. In other words, we did multiple exercises. We tried OCR, we tried visual language understanding. We tried many things. And you saw the strength and weakness of those models. Now, the state of the art in document AI has advanced quite a bit. And today, I would like to retrace the history of this field. This field is quite interesting. People have been doing OCR for a very long time. The two phases of OCR have always been, first, let us find the bounding boxes of text. Where is the text? Let's put rectangles around the text. Are we together? Around the letters. And then comes the understanding of what is inside the box. What is inside the box often can be treated as a simple classification problem. And where the text is in some sense somewhat like a finding. It's a segmentation problem, isn't it? Go put little boxes everywhere, bounding boxes everywhere that you have text. So it used to be a two-phase approach. That was the tradition. Given that tradition, we will look into obviously ways that people have done segmentation because it's a part of it. And then the classification or the understanding was after that straightforward. The limitation of that approach is that when you do things like that, you sometimes miss the totality, the complete. In a page could be a table, it could be a figure, could be text, all of which collectively are conveying to you some information. Okay? The semantics is sort of spread across these two things, and all of them together help you understand some point the author is trying to make. And those traditional approaches, as you know, they don't do very well with it. They do terribly with tables and so on and so forth. So today, we will ask this question: can this be approached as a computer vision problem and visual language understanding problem? Today, the way we understand document AI is we treat it as a visual language understanding problem. One of the authors of the DeiT 3 version, which we'll cover today, put it beautifully. And I love the phrasing that the researchers gave. They said, can we treat images, the document that you're trying to understand, the image itself, as a foreign language? As simple as that. With all its pictures and whatever it has, can we just treat it as a foreign language that we are trying to understand? And that, to me, captures the essence of how we like to think about this field today. When the input itself is simple text, direct text, you know it is text. You can use your BERT encoder and so on and so forth. But when it is an image, at the end of it, the summary that you'll find, which we are leading towards over and over again through these different papers, they will all try to cut up the image and do things such that it, in effect, becomes tokens of a foreign language. Right? Now, the authors of the DeiT paper explicitly use that language, but I would like to take the liberty of saying that broadly, it describes the spirit of a decade of work or a lot of work that people have been doing. So I'll start with the historical paper. Today, this paper, as you notice, goes back to, and the reason, why am I going over this paper? The reason I'm going over this paper is because it sets for us a backdrop of where we are starting. This is 2014. Do you notice that paper? 2014 was the time when you only had CNNs, and CNNs were the great wonders. We had AlexNet, right? ResNet was just coming onto the scene. That was also the year that using CNNs, we had the first generative models, namely the variational autoencoders, DC GANs, DC variational, and then, variational autoencoders using convolutions. And we had GANs, generative adversarial networks using GANs. You could begin to create little faces, right? Today, by today's standards, they don't look that impressive. But in 2014, the very fact that it was possible to do that was absolutely astounding. So with that as a backdrop, let us go and read this paper that now, at least in its fifth version, is exactly about 10 years old. You notice that we're October 2024. So let's read this paper and see what they're saying, because it will give you a sense of where things were. Now, I'm not going to read this paper in complete detail, but some parts of it is there. Today, we are going to read a lot of papers, retracing the history of the field. Now, if you remember, we already did visual transformers, right? Now, we are going to do a variant of the visual transformer called the DeiT, and then a BEIT, the third version of it. We are going to do a transformer-based OCR. We're going to do Nougat. We're going to do polygemma, and we are going to do DETA. DETA would be sort of doing what this first paper does, but without needing, but using a slightly different approach. So with that, let us get started. Let us get started. And we'll end with polygemma. It's one of the state-of-the-art models these days. A lot of these papers, they tend to come from one of three companies, either DeepMind or Facebook's AI Research Lab or Microsoft. So I apologize. I wish I had a wider spectrum of papers, but in this field, these people have fairly dominated the landscape at this moment. So we'll read this paper carefully. Now, I'll also give you optional lab work, which would be worth doing towards the end of the day or through the week. Otherwise, you're going to encounter those labs in a more serious way in the fine-tuning course. Just as a show of hands, is there anybody here who's going to be there in the RAD course tomorrow? You are. Okay, good. Nice to see. Nice, you'll see there. So in a way, it's good. Today, the heavy lifting in this course will be over. So from next week, you'll have other things to worry about. Okay, so let's read the abstract. Object detection performance. What is object detection? Let's unpack this paper slowly. What is object detection? Just to set the vocabulary, what is it? It is in a way recognizing that that's a cow in the picture. That's a girl, right? That's a bird. That is object detection. Now, object detection obviously has a hierarchical nature, because suppose it's a person, the person has a face, and so on and so forth. You could look at it like that. So rich feature hierarchies for accurate object detection and semantic segmentation. Semantic segmentation we have encountered. It is breaking up the regions of the picture, putting boxes. So, okay, let's start. Object detection performance as measured by blah, blah, has plateaued in the last few years. So this was 2014. What does that mean? The prior techniques had pretty much run out of gas. They weren't getting any better results. The best performing methods are complex ensemble methods that typically combine multiple low-level image features with high-level context. Are complex ensemble systems that typically combine multiple low-level features with high-level context. Yeah, font more, huh?
Yeah.
Okay. Let me see. Is that better?
Yeah.
Okay. So, what are ensemble systems? Ensemble means it's a word that roughly maps to a bag of, collection of, right? So, for example, when you have a symphony, you have an ensemble of musicians going at it. And the music that comes out, the symphony that comes out, the harmony is the net result of all of them working together, right? So, for example, the violin might sound wonderful, but with the piano and with the rest of the things and all of that, I suppose it sounds much better and creates the whole symphony. So that's the meaning of ensemble. In AI, what it means is sometimes a task is done by taking an ensemble of many methods. Right? A classic example is when you do random forest, a random forest is an ensemble of trees. Trees, isn't it? You take a lot of trees. For example, if you want to classify data, you take an ensemble of trees, lots of trees. Each of the tree is making a prediction, and then you do bootstrap aggregation. In other words, you aggregate the result, you take the vote. What is the majority vote? Is this forest, are all the trees leaning towards a cat or a dog? Isn't it? And why does that work? Well, that's the whole theory of ensemble. It's the wisdom of crowds. That's the meaning of ensemble. So what had happened is, before this paper came out, this paper, by the way, is, again, like these papers that I'm going through, these are not, these are truly landmarks in our field. They're genuine landmarks, big landmarks. It is really something you should pay a lot of attention, knowing, right, and doing. So it's important we do that. RCNN it's hard to believe that one can be an expert in the field, can be an expert in this field without knowing RCNN. So we'll start with RCNN, even though this is now of historic value. RCNN was followed by fast RCNN because those guys didn't quite want to yield the floor to transformers. They believe that transformers, my goodness, how much resources they consume. And CNNs are really good. So they put up a pretty good fight, fast RCNN, which did well. And then they came up with faster RCNN, which did even better. And they went on to show that, look, it does better than the transformer methods. But I don't think after faster RCNN, anybody created the fastest RCNN, right? Because more or less we now know that generally it's a good idea not to ignore the transformers.
Exactly.
Yeah. So we are in the world of transformers. We do bring CNNs, convolutionals, but we don't ignore the attention layers at all. For all the reasons that we have studied about attention, the virtues of attention. And so we'll get an example to study. This paper's value is that in a time when, believe it or not, CNNs were not being used for object detection, it brought about the great value of using CNN for this task. Remember, this is 2014, right? This is 2014. So you can imagine how much has happened in a decade, isn't it? Right? So in this paper, we propose a simple and scalable detection algorithm that improves mean average precision by more than 30% relative to previous best results on a benchmark, achieving a mean average precision of 53.3%. Right? MAP, mean average precision. We talked about it when we were talking about RAG, isn't it? And so you know that concept. I won't repeat it. Our approach combines two key insights. One can apply high capacity convolutional neural networks, CNNs, to bottom up region proposals in order to localize and segment objects. Two, when labeled training data is scarce, supervised pre-training for an auxiliary task followed by domain-specific fine-tuning yields a significant performance boost. Today, I mean, it almost seems this is the way you would do it, but at that time, it was quite a big deal. And I wouldn't go into comparing and this and that, but let's see how do they do it. Features matter, obviously. In computer vision, the way people used to do is they used to use two techniques called sift and hog. Right? What they would do is they would look at an image and find important features in the image. Right? Like, for example, if you have a building, the tip of the tower, the so on and so forth, they would look for significant features, right? Image features. And hog is the hierarchy of Gaussian. So they would look at this, and hog is right. I think that's right. Yeah. But if you look at performance on the canonical visual recognition task, so there were certain things. It was generally acknowledged that progress has been slow during the last few years, with small gains obtained by building ensembles, etc. Sift and hog are blockwise orientation histograms, a representation we could associate roughly with complex cells in V1, the first cortical area in the primate visual pathway. So what people used to do is they used to think, how are these images being projected into people's brains, and what should the neurons be doing in the brain, trying to recognize it? So I will gloss over some of these things. It suffices to say, and the only thing we'll focus on is that how are we doing it here? The way this paper went about doing it, object detection. So we'll read the figure. Our system takes an input image, extracts around 2,000 bottom-up region proposals. So its job is, using CNNs, propose certain little boxes all over the picture, 2,000 of them. Now, obviously, 2,000 is a bit of an overkill, right? Compute features for each proposal using a large convolutional CNN, right? Then classifies each region using class-specific linear support vector machines. So you need to figure out what each region is, right? So you use a classifier. So you see that thinking, box, and what is in the box, a classifier to tell what's in the box. That was it. RCNN achieves a mean blah of 53, right? For comparison, it does much better, right? Let's just say that it does much better. To give you, so this is a little bit of historic perspective. Fukushima's new cognitron, a biologically inspired hierarchical and shift invariant model for pattern recognition, was an early attempt at just such a process. Fukushima's new cognitron, by the way, is an influential line of thinking and approach in computer vision, and people who have done computer vision historically, they encounter this. It's a framework to reason about it. The neocognitron, however, lacked a supervised training algorithm, etc. Now, I won't go over it. I will just leave you guys with the thing that it has been trained and so on and so forth. In its days, it did very well. But the basic thing is that out of all those boxes, you had some way to determine which boxes you care about and which you don't care about, and which ones therefore lead to some good images, yeah, good things that you use a SVM for. Now, you could almost see, do you see this is 2014? In those days, support vector machines were still doing very well for computer vision tasks. In fact, they were doing so well that if you ever pick up a textbook on medical images of those times, you will notice that those textbooks on medical computational handling of medical images, MRIs, CT scans, X-rays, they had support vector machines as a dominant method, right? So it was support vector machines, and then gradually CNNs started coming by. Right? Yeah. So bounding box, based on, so you can figure out what are the correct bounding boxes. I won't go into it. This paper I'm mentioning purely for historic reasons. You notice that I'm not going into too many details about this paper. There is a bit of obviously computation. How do you determine? It's a regression problem, finding the bounding box. Why is it a regression problem, a bounding box? Because a box is given by, uniquely determined by what properties? If I just take two opposite points, for example, if I were to take this point, this one, x1, y1, and x2, y2, is it sufficient to draw this rectangle? Okay. So long as I tell you it is aligned around the x and y axis. Of course, right? So you can do that. That's why. And predicting a number is what? It's a regression problem. A machine learning model that predicts a number is a regression problem. And after you put a bounding box around something that you think is a thing, what do you need to do? You need to pass it through a classifier. In this paper, like when you read this paper, you begin to wonder, why didn't you just use a CNN for classification itself? Isn't it? Right around that time, AlexNet, ResNet, etc., were coming out as very good classifiers. But anyway, that's a lot of history to it. And you see the evolution of ideas. So I'll leave that paper there, and suffice it to say that with that in place, I'll take you to, just as a recap, remember what was the approach used in Vision Transformers, VIT, an image is worth 16 by 16 words. It basically said, you can take an image, you see this image, and we did that last time. You can break it up into 16 by 16 patches and treat those patches as just tokens, or feed it into an encoder, think bird style encoder, isn't it? With position embedding, just the same thing. And what comes out, just treat it as though you're talking natural language, you're talking about English. And the rest is, that was the key insight. That's all it was, right? Now, this paper was published by Google, used a lot of images, and the only trouble is they released the paper, they didn't release the images, the data set it was trained on, because they said, no, these are our images. So you couldn't train your own model, but they did release the model to open source. So this was oddity, because it is, then what happened is a similar approach was taken by Facebook then. Facebook basically said, okay, let's try to do the same thing, but this time we have images too. We also can do this game, right? And this paper is interesting. It is called the DEIT paper. Why is it called DEIT? Can you guess? Data Efficient Image Transformers. Right. So let me write it down. This is the famous DEIT paper. Data Efficient Image Transformer paper. Right? What it did is, it said, hey, we can be a little bit smarter and we can actually train a pure transformer-based system, but we can train it with far less data than DeiT was trained with. We don't have access to so much data. What do? We need to be smarter about it. So they did the same thing, if you notice. So if you remember the VIT, BERT always takes a class token in the beginning, right? Then they had the patch. So here's your 16 by 16 patch tokens. But notice that they have suffixed, again, a placeholder token called the distillation token. What in the world is that? We'll figure it out. And they passed it through this whole machine, your encoder, right? So this is your basic encoder and encoder, transformer encoder. Remember, attention, transformer encoder. So self-attention plus feed forward, a few layers of it makes it into a encoder part of the transformer. So what will it produce? It will produce lots of tokens, but in particular, it will produce the encoding, the hidden state of the CLS, and it will also produce a hidden state of this distillation token, and then hidden state of the image tokens, HI, isn't it? You use the CLS to train it for a cross-entropy. What does this term mean? Loss with a cross-entropy, CE. By now, you should be familiar whenever you see it in research papers. So cross-entropy loss, which is, you say, yeah, that is just like me. I'm used to it, isn't it? But notice that there is something else out here. Loss with respect to a teacher. So who is the teacher? Here, this teacher is actually coming from a CNN. So while DeiT completely eliminated the CNN, what this paper said is that, hey, look at this. When you just take a transformer, and so pay attention to what I'm saying, a transformer has no inductive bias. Remember, with the CNN, there are certain advantages. A transformer is a general purpose machine. Every token can pay attention to every token, but it is not at all informed that neighboring tokens are related, isn't it? But a CNN knows. CNN has a locality bias towards locality of features. It has a bias towards, there's an inductive biases there that features are hierarchical in nature, isn't it? That they have a translational equivariance, many other such things, right? So what you do is, you do something, what these people did was something pretty smart. They used a CNN network, right, through which the image also went, which they haven't shown in the picture, to produce a token of its own, right? Which token was used to tell whether it's a cat or a dog or a bird or whatever it is, right? And first of all, a CNN was trained as a classifier, so then it will become good. Whatever vector it produced, a hidden state it produced, you treated it as a, now see, this will produce a hidden state vector from this transformer, isn't it, encoder? But you teacher being the CNN, you compared it against the hidden state coming from the teacher, right? And what was it predicting? So you try to make this transformer predict the same thing that the CNN was predicting for an encoder. And the idea was that then you take the best of both the worlds, isn't it? CNN with this inductive bias, you take it, and transformers, it was a growing realization that for a whole variety, much more general purpose tasks with images, transformers would take over. So now, in effect, this paper used the benefit of attention, the core engine of transformers, the transformer encoder, as well as the CNN to train the transformer better. When they did it, so this is the DeiT paper, the results were very good, actually. And suffices to say, I won't go through each and every part of the result, but this is the main architecture. Guys, do you understand the architecture of this paper? Yeah. This picture says it all. Yes, go ahead.
So I'm paraphrasing, just so that I understand. So the question is on so CNN will be trained separately.
Yeah, a separately trained CNN. That's why you call it a teacher network. Because some CNN is very good at classification. You're now trying to transform it to do the same thing.
And what is the outcome of that? So first you've taken an image, you broken it into 16 pieces. Then you have the attention, it's a CLS, and there is relationship. Yeah. Now the CNN has said that the whole image is particular class.
A dog. A dog. Right. So now it says, suppose you say the probability, so it comes with the probability of a dog. Let's say that the CNN says probability, okay, let me use a smaller font. Probability of dog is 0.97. Your taken says probability of dog is 0.5. You just made a mistake.
Which one?
This token. So what can you do? You have now.
Can you just step back on that? The first one is what? The whole CNN? The two probabilities. Can you explain?
Was only the top one is CNN.
No, see, you see this L teacher. So what you're basically saying is, let me draw it out. First thing you do is you take a CNN, right, with the typical CNN architecture, etc., etc. And the last layer, you create a classifier. Yeah. Right?
All you get is a probability, right?
Yeah. From any encoder system, you'll only get at the end of it probabilities. Yeah. Right? So you get a last layer vector teacher, which you can feed it into a softmax and get the probability of a cat.
Yeah.
Right? Let's say I use the word dog, so let me use the word dog. It will also have a probability of cat.
Yeah.
Now, this machine is trained. You keep it. Now, what you do is you create this encoder network, transformer-based encoder. In particular, think bird-like structure. What do you give? Except that you gave it patches of images. So image patches, right?
One image.
Yeah, of one image. You take an image and you slice it up into patches. Remember, this was the message of DeiT.
Yeah.
You can 16 by 16 words. Now, each 16 by 16 patch can be thought of as a word, right? So you give these words of the tokens. Now, because it is bird-like architecture, you know that you're going to put a special CLS token here, right? And all they are saying is, just for fun, add one more token, which you will call the distill token, distill.
And is the same image sent to the CNN?
No. Yes. No. See, okay, wait a minute. CNN has been fully trained. Just follow through with this. So now, what is going to come out of this? You will get a hidden state for CLS. You will get a hidden state for each of the image patches, right? You will get a token for distill, hidden state for distill, right? Now, how do you train a typical DeiT, for example? How was it trained? What you would do is you would feed only this into a softmax, right? You would feed it into a softmax that would produce for you the probability of a dog, probability of whatever it is, and max means you pick up the highest probability object and say it is that. That's what you do. So if I were to just train it only using that, the DeiT paper trained it without the distill token. What did they do? They knew the answer because it's labeled data. And they said that if it is a dog, negative log of probability of a dog is my loss. This is your basic cross-entropy loss, CE loss, right? Cross-entropy loss, which is what you see here, the yellow thing that I'm highlighting here. That's what they're referring to, the cross-entropy loss. But the additional thing that the DeiT paper did is they said, okay, now wait a minute. We also have the benefit of taking this image of a dog and passing it through a CNN network, right? And it will also produce a hidden state, which we call the teacher state, right? And therefore, we can find out the probability. So what is it saying? It will also produce the probability of a dog. Now what we do, the way the distillation works is, you say that if the student, so your transformer network is the student, CNN network is the teacher. Now you say that the probability that I get, probability because of the hidden state, probability of a dog from the hidden state, from the distilled state. Remember, you're not using the CLS token. You already did that. Using the CLS token, you did the cross-entropy loss. But they're saying add one more term to the loss function, which is the student-teacher loss function. The student's job is to predict the same thing as the teacher.
So we always say that never break your thoughts. So we always say that, right? The purpose of CNN is it aligned with the images, okay, to semantic entry from the CNN.
Yeah.
Whereas transformer is from that they're getting the words and passing to the transformer, which is come first. I mean, making conclusion. CNN first or transformer first? Which comes first?
No, it is not a question of first and second, guys. I think, are we all getting confused about this? We are. Huh? Okay, let's go over this slowly. See, forget about transformers completely. Forget about transformers. You know that you can train a CNN to do image classification. Do you agree with that? Just train it. No more training. Keep it. It's a pre-trained model, a pre-trained CNN model. So for any image which is a dog, it will produce a certain probability that it's a dog. Right? Keep it in your back pocket. So here's the thing. From the CNN, from teacher CNN, you will get a probability of a dog. Now, this is the teacher probability. So far, so good, right? Now you are in the process of training your transformer. So think your VIT, vision transformer. What did you do with the vision transformer? What you did is, except for this distill token, look at the rest of it. This is your standard. Isn't this your standard vision transformer? All you did is, it's your standard transformer encoder. You just even the CLS token is there, BERT CNN token is there. You compared. Only what happens is that everything becomes vector, but you take the CLS token and as the input to a softmax. Right? Because CLS is a dummy token, so it's paying attention to every other token. You use it to produce the probability that it's a dog. Let us say that it produces, let me just call it probability. So from the CLS token, you produce the hidden state of the CLS token, right? And therefore, you produce the probability from the CLS that it's a dog. We agree with that, right? It's coming from the transformer encoder. Now, because we know that it is a dog, I can use a loss function, your standard negative log likelihood, cross-entropy loss, minus log probability of CLS of a dog. Why is that important? Because if it is a dog, the probability that it's a dog should be 1. Then the log of 1 will be 0, means no loss, no mistake. But if it says it is probability of a dog is 0.1, it's wrong and quite wrong. So log of fraction is always negative. Negative of negative is positive. So now you have a real loss, right? So this is the log CE, cross-entropy loss. Yeah. So far, so good, guys? Yeah. So this part is still what VIT did. Yeah. What this paper did is, it said, okay, let's also bring in a student-teacher loss function, because the hidden state of the distill token, because you added one more token into the game, and that token also becomes something. So one token is trying to align itself with the reality, with cross-entropy loss. Another token, what you do is you force it to learn from the teacher. So it will produce this probability of the distill of the dog, isn't it? Now what you do is you create the so-called student-teacher loss. Here they just call it the teacher loss. Means that this is the teacher. The teacher, because the CNN is the teacher. The CNN says the probability of his being a dog is 0.97. You're saying the probability of his being dog is 0.1. You're wrong, isn't it? So now you can do the student-teacher loss function, comparing this value against this value. So 1 second. So now you have, so guys, follow through. You have two loss functions. If you minimize both, what will happen is, and this is how you do it, the student is independently learning from reality as well as learning from the teacher. Because there are two signals it's learning from. It's learning from the reality, but to learn from the why did we bring in the student teacher? Because to learn from reality takes a lot of data. Remember, DeiT said, oh, lovely, you can do it. Oh, by the way, you need lots and lots of data to do it. Right? And we are not going to give you the data. Here's a model, but we are not going to share the data with you. Right? So you can play a game. You can say, all right, distillation is one of the great contributions of Geoffrey Hinton, the paper of distillation. If you're in the foundational course, you'll learn about distillation. But I won't do that. Distillation basically means there is an alternate way to teach a model. You tell a model, forget about reality, right? I mean, they learn something from reality also, the usual stuff. I mean, don't forget about reality, learn something from reality, but your learning can be accelerated because I ask you to follow the teacher, right? And for teacher, you take a very powerful model, which you know works. And you say, make sure your prediction is the same as the teacher. Are we together? So then you get it right. I suppose I'm reminded of a story that is somewhat unrelated. So this is real actually. So Einstein used to go from place to place giving lectures on the theory of relativity. After a little while, his driver said, you know what? I have heard that lecture so many times that even I can give that lecture. Right? He became a student. So they decided to play a joke. He says, okay, next time you go give the lecture. So the student went and confidently said, I am Einstein. Right? Because those people had never seen Einstein. Right? Actually gave the lecture. Everybody is clapping and brilliant. Right? And they're all in awe of this Einstein. The trouble is, then some physicists started asking questions. So when they asked a very tough question, he says, well, you know what? It is so obvious my driver will answer this. So that is student teacher learning. Yeah. So anyway, so the driver became a student because the driver was not learning from textbooks, isn't it? The driver was just learning to imitate the teacher. Yeah. That is distillation. In reality, in distillation, 1 second, you give two realities. You say, learn from the textbook, learn from the reality, which we are doing here. You see that we have a cross-entropy loss, but also learn from the teacher. That is complete distillation, right? You learn from the, well, the full version of distillation is even the teacher is learning, but has a bigger brain, right? So you have all three learning. The teacher is learning, the student is learning, and both of them are learning from reality, and the student is also following the teacher. But in this particular case, you assume that the teacher has learned. I'll take questions, guys. I know many of you have questions. So you assume the teacher has learned. It's a pre-trained theory. And the student only learns from reality using the cross-entropy loss term and learns from the teacher. Imitate the teacher, both. Are we together, guys? Right? This is classic distillation. When you do distillation, what does it do? It accelerates the learning, isn't it? And not only accelerates the learning in this process, you can learn from less data, right? So it is a data sparse regime of learning, which I believe they must have said somewhere in the paper. Let's go and see whether they talk about it or not. Okay, let's read this introduction. It's been many years actually since I read this paper. 2021. Recent neural networks purely based on attention were shown to address image understanding tasks such as image classification. Recently, neural networks purely based on attention. Who are they referring to? DeiT. Yeah, the 16 by 16 cube. These high-performing vision transformers, so nowadays you call them vision transformers. Right? Vision transformers are pre-trained with hundreds of millions of images using a large infrastructure, thereby limiting their adoption. Yeah. So you cannot, I mean, the problem is, it's very hard to train such models. What they politely don't say is, dude, you never gave us the images. So let's continue this. In this work, we produce a competitive convolution-free transformers by training on ImageNet only. That's a remarkable thing. ImageNet is what? The data set that Fifili created. Lots of every single thing: house, boats, cars, people, children, ducks, everything is there in the ImageNet. Right? We produce a competitive. Now they say convolution-free. Why are they saying convolution-free when they use convolution as a teacher? Because at the end of it, when the model is trained, it is just an encoder, right? What you take to inference is just the encoder. Right? We produce a competitive convolution-free transformer by training on ImageNet only, and that is the remarkable thing, right? That it's a publicly available data. We train them on a single computer in less than 3 days. That is the remarkable thing. You realize that something that was big science, a big engineering, just became feasible at a reasonable scale in this paper. Right? Our reference vision transformer, 86 million parameters. By the way, 86 million, these days when people talk in terms of billions, anything below billion is like almost shameful to talk about. This is 0.086 billion parameters, right? Minuscule model. Our 86 million parameter achieves top one accuracy of 83.1 on ImageNet with no extra data. More importantly, we introduced a teacher-student strategy specific to transformers. Teacher-student was the classic thing of distillation. It relies on a distillation token, ensuring that the student learns from the teacher through attention. Right? So we'll pay more attention. We'll go and read some of the details. Actually, I'm hoping that I didn't get the technical details wrong. I'm reading it after a long time. We show the interest in this token-based distillation, especially when using ConvNet as a teacher, convolutional network as a teacher. This leads us to report results competitive with ConvNets of both image and when transferred to other tasks. So they say that at the end of it, this transformer does as good as the state-of-the-art convolutional networks, which was the goal, right? To do it using transformers. So you can see the beginnings of bridging over from CNNs to transformers, right? So now let me go and make sure that I got the distillation process right. I got all the other parts right, I'm sure. Knowledge distillation. Okay, so let's look at this part. Knowledge distillation, KDE, introduced by Jeffrey Hinton, refers to the training paradigm in which a student model leverages soft labels coming from a strong teacher network. In simple terms, the student tries to imitate the teacher, right? This is the output vector of the teacher's softmax function rather than just the maximum of scores, which gives a hard label. Such a training improves the performance of the student model, etc. On the one hand, the teacher's soft labels will have a similar effect to label smoothing. On the other hand, as shown by Wei at all. By the way, Wei, you'll see a lot of papers from Wei. He's a big deal. A teacher's supervision takes into account the effect of the data augmentation which sometimes causes a misalignment between the real label and the images. For example, let us consider the image with a cat label that represents a large landscape and a small cat in a corner. If the cat is no longer on the crop of the data augmentation, it implicitly changes the label of the image. Knowledge distillation can transfer inductive biases in a soft way to a student model using a teacher model where they have to be incorporated in our. So basically what they're saying is, let us say that two things. What is data augmentation? See, images, whatever they are, you always try to get more data because the more data you have, the better model you'll have, right? So what you do is you take the image and you do various augmentation techniques with images. Some basic thing is you'll slightly dilate it, you'll slightly rotate it, you'll add some little bit of pixelation, right? Gaussian noise. You will sort of move it around, translate it a little bit, crop it. Cropping is very easy. But imagine that in a big landscape, there's a tiny cat and you just crop the image. The cat may entirely be out of the image now, isn't it?
Yeah.
So you're giving it a label of a cat is misleading now. And one of the nice thing is, even though your cross-entropy term is still saying, hey, cat, cat, but at least your teacher network will say, not the cat. You see that, right? That's the advantage of it. Because the CNN, so that's what they're referring to, vision transformer overview. So attention, guys, this equation, I trust, does not need any further. Like this is like going over well-trodden territory, isn't it? This is all easy. We are the class token, fixing the position encoding, distillation through attention. So yeah, let me just go over the technical details of how they did with the distillation. Mimics the Kullback divergence between the softmax of the teacher and the softmax of the student model. Okay, so this is the right thing. I get what I told you guys is the right thing. So I'm saying that you make a loss function between the probability distribution that the teacher produces and the probability distribution there. So in explaining, I just said that let's say that the teacher produces a probability of dog and the student produces a probability of the dog. You want to align these two, right? The more specific way actually is the proper ways. The teacher doesn't produce just the probability of the dog. It produces the probability of a cat, probability of a horse, cow, probability of a cow, everything, right? So it is, in other words, a discrete probability distribution. It is a softmax, right? The output of the teacher is a softmax. It will give you the probability of every item in your dictionary. And when you compare the probability, this also will produce exactly that, a P student for everything, for this, a P student for cow, right? It will produce all of that. And what you want is, if student has to mimic the teacher, each of the probabilities should be close, right? So the measure of loss between two probability distributions, the common one that people use because it's easy is the KL divergence. KL divergence, which is something in the foundational class I teach you, KL divergence. Basically, it means that if this probability looks like this and the other probability looks like this, how far different are they from each other? Yeah. So KL divergence, if you remember, it's not called distance because it's asymmetric. It doesn't fulfill the criteria of it. Why KL divergence? Because it's the most common one used over the years. Could you have used something different? For example, could you have used the Earth-Mover's distance, the Wasserstein distance? Surely you could have used that, right? So don't get hung up on the KL itself. It is some measure of probability difference, right? Create a loss function out of it. KL is pretty common. That's all it is, right? So now let's pay attention to this equation. Does this look scary? Right? It is actually, so let's unpack this because if you get it, it won't be that hard. So see, suppose I have a pie and I say 30% of the pie is here. Lambda is 30%. So what is the rest of the pie? 1 minus lambda, right? Yeah. Isn't it? So if this is 0.3, you would agree that this is 0.7. So you're basically saying See, I have two loss terms.
Hmm.
Now I have a hyperparameter to worry about. Which one to focus on more? So you can say, forget about the reality. Just make the person imitate the teacher. Like that chauffeur for Einstein. It gives a perfect lecture. So then you're only focusing on the KL divergence loss because there's the teacher loss, the second term. On the other hand, you can say only focus on the reality, forget the teacher. But you want to actually dial between these two in such a way that you get the benefit of both of them. So you'll have some hyperparameter, how much to consider the teacher and how much to consider the reality. So lambda 1 minus lambda is explained, isn't it? Easy. Then you also have, because it is scale divergence, you have something, what you do is, it has to, in the distillation process, there's this whole theory called temperature, right? Actually, how about this? Why don't I explain softmax and temperature as a sidebar? But I'll do that. But what it means is that, I'll give you a simple intuition. If I take this probability distribution and I imagine that it's a sandhill, right? And I sort of squish it down, uniformly squish it down. So this becomes slightly flattened. And this also gets slightly flattened, right? So now, in the extreme limit that you completely flatten it, they'll look similar. Right? They'll begin to look pretty similar because they'll won't be zero everywhere, uniformly, more or less zero. But temperature essentially is a measure of how much you're flattening it down, each of the distributions, before you're comparing it, right? That is the notion of temperature. Temperature comes again from physics because these equations have come from physics. This is quite literally coming from Boltzmann machines and arguments from that, right? And those of you who are doing the foundational course, the good news is that's quite literally coming up next week, right? In honor of the fact that Hopfield networks and et cetera, and has been quoted as part of the Nobel Prize, I'll be covering that too. Obviously, I was going to cover it anyway, but that is it. So now does this equation look easy, guys? Right. It's just written with psi and so forth. The psi is the output, the psi is the softmax function, that's all. So this is it. I won't go more into it. So now does this paper make sense?
Perfect.
Right? And so what is the main thing they're saying? They're saying, you know what? What is the main contribution of this paper? They say VIT is a great idea, but only Google can do it with its hardware and its gazillions of images. We are going to democratize it, isn't it? We are going to make it possible to do on one machine in 3 days and with less images. Right? Just imagine it, public image data set. So that was the contribution of DeiT. With that in place, oh, it's 12:30, guys. Food is getting cold. I'll just stop it here. Have your lunch. Can we make it a very quick lunch, guys? But can I please request that you go and read this this paper? So I should add it to that. But just take down the title. I'll just leave the title here. Google this paper up. It's the famous DeiT paper. Would you mind please reading through it? Review it during your lunch. We'll meet at 1 o'clock.
Yep.
Yeah. Awesome.